All right. So the title is kind of catchy, I guess. So predicting under the curse of rarity. So that's what we're doing. Right. And then, so I have a large group, but today's talk is mainly the work by Benjamin Stoller, Ben's thesis work, and then Ingrid's also thesis. So Ben just graduated, and Ingrid is about to graduate soon. And then also a very close collaborator and my former student, John Francis. Okay, let me start with this question. So this is a much broader question. So can data solve all the problems? So uh, I think this is a question that comes up in every panel these days. So do you all believe in data? Are you a believer? Okay. So so I think data is needed so that everyone agrees, but can data solve all the problems? And is that the only way? Then the data-driven approach that is really focusing on this in distribution, in domain approach makes sense because that's the way to cover the majority of the space that's covered through this data. So this is a great mainstream idea and it makes sense. But there are very important problems where data is very rare. It's in fact, some of the data is, very hard to create as well. So safety critical domain is one of the examples. So we know there are very little data in that space, but we can't collect new data because that means we need to really create accidents. And then there are other domains that are also kind of important to humanity, but we don't have a lot of data. So I work on navigation, but I also work on some other space where we share the pain so there's no data. So the making things, so this kind of activity is very unique. So why is painting or writing letters on a paper so special? What is special about these creative activities compared to pick up a bottle and move it to the right, or folding towels? So that may be more useful skills to assist the people, help doing the real job, like do the cleaning work. But at the same time, these tasks are much harder in a way, like in a very special way, because creating something means the observations are seeing something that's new. So that didn't exist before. And in the next state, it just popped up. So I think that is a very intriguing point of this creativity space. But anyway, so this is the domain that we do not have a lot of data, especially in the incremental, like adding action and then seeing the sequence. But like today's topic is more safety critical domains. So I will start with the self-driving and then I'll show some examples in aviation as well. So this was mainly Ben's thesis work focusing on self-driving, and then Ingrid's also worked on self-driving as well as aviation. So these two examples to show were like rare examples of autonomous vehicle getting into a accident. So there were no fatalities. So I'm just showing these two examples. So one, the autonomous vehicle just randomly stopped, causing multiple vehicle crash. And then the other example is a real rare case. So there was a delivery robot on the sidewalk, which was hit by another autonomous vehicle. So, but in order to learn very robust behavior against these safety critical scenarios, the model has to see some, similar cases. So that's the issue. So how do we address this issue? Like, data, maybe we need data, but there is no data. So we want to like look at the existing data again, just in case there is a different way to utilize the data better. So the first idea was kind of looking at the existing data, but trying to label them. And surprisingly, this like gigantic data in self-driving were just a bag of data. So all the scenarios were in one huge bag because they are all benign cases. But we looked at these benign cases, just in case there are maybe little safety critical examples. So the idea is maybe we're training using very common benign set, but maybe we can create this unseen set that's much more complex, and it could have been a disaster. So, okay, so how do we do this? So there were some existing approaches, which is more rule-based. So, okay, if the cars were clustered together or if the density is too high, then, you can flag them as maybe safety critical ones. So we also came up with some heuristics to do so. And then what we added was this counterfactual probing, which means, these are maybe this is the one car is changing lane, but in reality, the other car, the red vehicle, kind of slowed down, so nothing bad happened. But what if that car just went a little bit faster? So kind of taking existing scenarios and try to kind of generate like what if scenarios. And then if one candidate scenario can lead to many possible kind of bad cases, to our purpose, for our purpose, that's a good candidate. So we want to kind of use that as another scoring way. So we determine this scoring function and then kind of have a final score. So we were able to kind of split these data, existing data, into some subsets. So qualitatively, you can see the difference between the top row and the bottom row. So that is kind of the split that we were able to create. And then, so in order to measure like whether the generated data will be useful, we did some like distribution checking. So this was the original distribution from the Waymo data set. And if our idea works, then we should be able to see the distribution shift, right? So that's what we were sharing. So the score, higher the score, the more safety critical the scenarios are. So we were able to create this kind of a shift within existing data. And then as a result, if we test existing prediction algorithms, then if we just split randomly like half and half, then, seen and unseen, they're all same distribution. So you don't see performance difference. But what we are saying is we have two kind of different approaches within this safe shift idea. So the basic one, you see the safety critical, the collision rate goes up because of that shift. And then by adding a little more idea, we get also a higher shift. Okay. And then this next part, I'm going to kind of advertise the toolkit. So in case anyone is interested in trying out this scenario generation or scenario characterization. So this is open source tool. So the idea I just described is kind of follows through this pipeline. So taking the existing data and then try to characterize the scenarios into multiple possible ways. And then it also provides very nice like visualization tools. So the characterization layer is doing exactly the probing idea. So taking the existing candidate and then kind of do the probing. So just in case this can lead to safety critical scenarios. And then so, and these are nice, like nice visualization tool when that comes with the thing. Okay. And then also in the original shapeshift, we only did the binary, and this can be used to create more categorical subsets. Okay. And then there are many applications you could use this toolkit for. So I'm going to just a little bit. And then there is an open source link. So maybe I can share it later in the slide. Okay, so the next part is, so we now know we can maybe scoop out these more useful like scenarios from existing data. And the next part is kind of natural follow-up. Okay, can we use this a small set to synthesize similar data? So that was what we are trying. And again, there are some existing data to synthesize and generating this crash idea using maybe mainly rule-based, knowledge-based approaches. But the difficulty is just creating these random scenes. Actually, you can easily create crashy scenes. It's just, just go into the intersection and then crash. So it's easy, but a lot of them are just very unlikely to happen. So not very useful. So it's highly safety critical, but very unlikely to happen in real life. So so it's this is another kind of couple of existing work that's using resim. So kind of sharing the same intuition. Let's start with existing data and then try to maybe generate safety critical ones. So, but again, regenerating, but in a realistic way, it's turned out to be very hard. So these are the existing scenario generation algorithms, and they somehow chose the names of animals. So this is an algorithm cat. And I mean, this is very safety critical, but it's very unlikely to happen. So this could happen, but the chance is very low. So the car kind of is aggressively is trying to crash your vehicle. So, and then another vehicle is just randomly kind of crossing the center line to the head-on collision. So the other algorithm is called Goose. So our algorithm is a seal. So yeah, yeah. So the seal uses this learned candidates and similar idea to the counterfactual proving. So and this so the difference from the previous safety shift idea was the very first one was more heuristic idea. So we also designed some nice features to collect these scenarios. And SEAL is more data-driven, learning-based approach. So selecting the candidate was the first step that we trained to scoop these nice candidates using this proving idea. And then this the second idea is like, so we have nice candidates. So these have great potential to generate these disastrous scenarios. But the second part is how. So the how part is, okay, it has to be safety critical, but at the same time, likely to happen. So for that part, we leverage the existing ideas to learn these many driving skills. So not necessarily all bad ones, but turning, going straight, turning right. Those are all driving skills. And then we realized that there were some adversarial skills as well. Like we sometimes have to cut and change lane a little bit in an unsafe way, but we managed to do it. So those were the skills from the data. So it is a naturally seen skills, but combining with this great potential candidates, we can generate like very nuanced, reactive kind of behavior. So again, so this is a performance wise. So we have to show two things. Okay, so still is better, meaning that these are more useful to train a more robust policy so that performance is measured in the ego vehicle's performance, like did it make it to the goal? So that's it, improving. And then the other one is a realism. So this part is still a open question. Like, how do you measure whether this is realistic, natural? So on this paper, we were using something like a Wasserstein distance that was used for measuring the naturalness in like gain, real or not real kind of a thing. But this is an area that we keep brainstorming ideas. So if you have good ideas, I think that's a great direction to pursue too. Okay. So the third idea was still we weren't like fully contented with the behaviors. So sometimes the SEER also created this very unrealistic scenarios. So this idea was using what if we use some of the real crash data. So this is but there was not much data, but we found this SUTD data, which is like YouTube video, like examples of the real accidents. And using this, we were able to extract the trajectories and then label them. So the idea was, okay, can we use this small, very few examples, but labeled ones to fine tune the model? So in the kind of a separation space, you can see if we don't do anything, then everything is mingled. And safe shift, the earlier idea, we're able to kind of separate these different types of scenarios. And then using this real crash data, we were seeing little more split. So visually, it's kind of meaningful. And then this is another comparison. So even still creates a, I don't know why this doesn't play. But yeah, so it is supposed to be a video. So SEAL also does this ego T-bone and the SEAL plus real data fine-tuned version creates really, really nice, very wow, this near miss kind of cases. So unfortunately, the video doesn't play. Okay. And then again, like quantitative result, we have to show these two things, the success rate and some realism score. So this again, the metrics are the difficult part. So again, like we are using these, but these are not the metric that everyone should use. So you should continue maybe proposing new idea, better ideas. Okay. And then this is another way to show our results. So this graph is a little bit confusing, so I will try my best to make it a little bit clear. So the collision casualty, so one bar goes down, one bar goes up. So what does that mean? So the important one is the near miss that goes up. So we want to see more, wow, that's dangerous, but maybe not like the real collision. So near misses are important cases we really want to generate more. So that's a good sign. And then the other two is kind of different category. It's in the same table, but what we need to see is the kind of the we want to see similar size bars on both. So if you see compare, the blue has a kind of imbalanced part. So one is adversary kind of striking ego, and the other is ego striking the adversary. So we want to kind of see more or less equal numbers. So that's it. That's a good result, even if you see the flip. Sorry. Okay. All right, so that's what it is. And then the other one, again, it's kind of confusing. So I kind of put the circle there. So the one in the middle are the ones that we want to see less. So because they are too aggressive. So they're super safety critical, but they are rare things. So even in this part, we also want to generate like most likely safety critical scenarios, which are the glancing and near misses cases. So they should go up, but the other we still want to keep it down. So, and this chart will change in the next work because that maybe we have enough near miss. So these are all calibrating kind of effort. So these are okay. And then the next part is quick introduction of this problem because it is a less known issue. But the general audience is more aware now because of the recent accidents. So we've been working on this project for several years. So whenever we look at the data, we see a lot of near misses near the airports. And then we were aware of this labor shortage or, understaffing on ATC. So I know everyone flew in and going to fly out. So, I mean, it is pretty safe space, but there is some concerns because of many accidents. So these are like before this article, like New York Times wrote an article about near misses, but before that, people didn't really know because unless there is a real collision, they never make news. And then it's so frequent, we can't really make it an announcement. But FAA, which is an organization that kind of keeps track of these data, they have a categorical score. So 1, 2, 3, 4. So like 3 and 4 are, wow, that could have been an accident kind of a thing. So, yeah. And then in the recent years, we were actually seeing the unfortunate, like really bad cases. So this is very, very important problem. So I know many of you are working on pedestrian space. So even if in that space, what's even if there is a collision, we rarely see fatality, right? And then in self-driving, it could be much worse. So safety becomes much more important. And in aviation, the magnitude is just it's a different category, right? So it's important, but not many people are working in this space. So it's anyone working in aviation, like social navigation in aviation. So yeah, so I'd like to kind of bring that up because we also have a data set and toolkits so that people can try out. So these are some of our work how to and like turn this into a little bit safer space. This one was the maybe the only approach that we actually tried the decision making layer. So you will see all of these pedestrian or self-driving in aviation. We were only able to evaluate our approach in prediction tasks because once one agent makes a decision, we can really generate the other agents. So in sim, it will be always kind of synthetic. And in real, it's also very hard. Even in the pedestrian space, if we hire people, they know they are a part of the game. So it's never kind of yeah. So if anyone comes up again with a great idea to set up a test bed for these problems, it will be great. So for this one, we had the simulation environment. So everything was in simulation. So I'm not going to go into any detail, but this is a decision-making algorithm that's using the socially compliant prediction algorithms inside. And then the highlight was we did the user study. So we hired 13 to 15 the real FAA certified pilots come to our lab and ran these 1 to 2 hours actual simulation study. And then the setup was very similar to a Turing test. So there was a war. So the pilot come in and then fly with another pilot on the other end. And they don't know if it's an AI pilot or a human. So And then we gave a survey question, so ask a lot of about the other pilots' performance. Did they follow rules, or that kind of question? And then we also included the Turing question, like, do you think it's a human or not? So the quick result is the Turing test. Like, when was it invented or proposed? It's from 1950. So it's a kind of a method that, wow, is the AI like good enough to pass as a human? So that's a concept. But the people's like perspective or the observations on AI performance has shifted. So what we are seeing is in maybe 1950, people thought that, oh, AI must be bad. Okay. So AI cannot be as good as human. So that's the reason, like, oh, that's a machine because it's bad. That was the idea behind the Turing test. And then what we saw was it's a 50-50 split now. So some people thought it was AI because it was bad as before. But the other half said, okay, it must be an AI because it's so good. Okay. It's so good. So, and then some people said it's a human. Again, 50-50 split. It's a human. They're very good. So that's the original Turing test kind of idea. The other half, it's a human. Look at them. Like cutting the line, but like ignoring the rules must be a human. So that question alone doesn't carry much meaning anymore in this context. So the competence matters much more. So even if the behavior is like robotic, like you can see this is a robot, but they follow the rule, they behave in a very predictable way. So they really like the predictability because it's really has to be safe. So if you can predict, it's a danger, right? So those came as a very, very important characteristics. And then just comparing the performance overall, our proposed algorithm was comparable with the human pilot, but this because of the scale and the setup, like how much simplification went into this study. This is only the result that's scoped within this simple setup. But I find the other results much more interesting and insightful. So I'm sharing that instead. So, and also people don't really care much about natural behavior. So I think that changes, and this is the like very, very high safety critical domain. So those are more or secondary. So anything that will make the behavior safer by, okay, I'm going to straight and then like show the light, they much prefer that. So competence is a much more important than explainability or other things. And then and by the way, this kind of survey result is very consistent with the self-driving side as well. So, okay. So, yeah, I think this might be the last one. So, again, it's a relatively new data set. So, we have 42 US airports, and this comes from the real data. So, the swim data is a very raw, unfiltered data, and then we already post process everything. So this would be hopefully this will be a useful tool for researchers who want to try out, social navigation idea and prediction algorithms on a slightly new domain. Uh, okay. Okay, so some takeaway. So, this artificial distribution shift was possible from the existing data. I think that was a good one. And then the modifying the existing data to synthesize and creating scenarios turned out to be useful in training because it's kind of likely, but it's much more safety critical. And then also there was a kind of secondary one. So even if the quality of generated data wasn't that great, was still helpful. Even if it's not perfect, it's better than not having that data. So, so I'm kind of leaning in more broad way the approaches that are relying on heavily on simulation. It's never, I mean, never is too strong, but it'll take a long time to have a really, really good simulation environment. But based on these experiments, what we see is even if it's not helping, if it's not like completely same as the real situation, close enough data is still very, very helpful. So using simulation or synthetic data to fill that gap is a highly recommended method. Okay, and it's a debatable topic, but you can argue. Okay, and then the third one is evaluation. So I mentioned a few times during the talk. It's a frustration point because we can develop a lot of good algorithms, but at the end of the day, we have to show, okay, mine is better than others, but how? So those metrics are, in a way, limiting our, you know, the freedom to explore more space because that's harder to evaluate. So I think this is a thrust area that maybe some people should spend more time. So if you are very good at designing like benchmarks or evaluation method, I think there are many upcoming grant calls really supporting this trust. So I think that would be great. Okay, that's it. Thanks for your attention. Thank you.
Very much.
Mm.
So let's take one or two questions. Yes, and then you. Yeah.
So thanks for the great talk. Super interesting stuff. I'm curious about this table with the performance of the ego policy, so the autonomous driving part, and comparison with the realism with the Wasserstein distance match.
Yeah.
This actually seems quite counterintuitive to me. So it's like, wouldn't you want to have your realism highest? So kind of be
Yes.
as
This is the
close.
distance, so lower the better. Yeah.
Yes.
Yeah.
So the lower the better the realism. So you want to be as much as possible in distribution to your data set, but have the lowest possible success rate. To kind of not generate unreasonable adversarial scenarios, generate kind of ones that are reasonable that make your policy fail.
I think that maybe we could see it that way too. But if the success rate is also kind of, this is another trap. So these two are the common metric that all the papers include. So this is a success rate. So I think the intuition is if the ego agent cannot make it to the goal, then it's bad. So
Okay, thanks.
Yeah.
Maybe I would have a quick follow-up. So is this evaluated in open loop or in closed loop? And if it's in closed loop, like what kind of traffic agent models are used?
That's a great question. So the agents are a little bit reactive. So so that's another chicken and egg problem. So we are trying to have that perfect model, but we have to rely on this other decision-making filler model to close the loop. So that is the difficulty of like evaluating and also going beyond the prediction. So beyond the prediction means if you change one behavior, you can rely on the data because everyone should react to that. So that's a kind of at the core of the difficulty. Okay.
Okay, thanks a lot.
Yeah. Mm-hmm.
Thank you for the talk. So I'm curious about part because I saw your metrics you shared, like with success rate, it's not like a fully 100% rate. I assume there are gonna some failure cases. I want to ask, it's possible that you add a soft constraint on that. Do you think it's important to integrate hard constraints to make the success rate much more higher? And for example, if we say a realistic trajectory maybe must be successful because it not collide, it follow traffic rule. So how do you think it's important, or how do we do that to add hard constraints into the generalization scenario?
Yeah, that's a great question. So safety critical domain, sometimes you have to fail because I don't know if I understood that part accurately. But what I'm saying is, my goal is to go outside. But if there are some maybe some people lying there, so I have to maybe attend to them, then I will fail my goal, but that is more important. So safety is in a way more important. So maybe that's what you're saying, like adding hard constraints. So you are optimizing for reaching your goal, but there are hard constraints. So you cannot violate to meet your goal. Yeah, yes.
So it means like if we have the evaluation metrics with measure how many times we collide with each other, the number should be like 0.
Then success rate should be 0.
The number of collisions should be 0, no matter what the success rate is. But if we propose the evaluation metrics which measure the safety, then should be as high as possible.
I see. So if it involves any collision, then they should get 0.
Thank
Yeah.
you very much.
Yeah.
Okay, that's it for the talks in the morning. Let's thank Jing one more time. And
Thank you.
let's close as well.